Welcome back to Machine Learning Guide. I'm your host, Tyler Ranelli. MLG teaches the fundamentals of machine learning and artificial intelligence. It covers intuition, models, math, languages, frameworks, and more. Where your other machine learning resources provide the trees, I provide the forest. Visual is the best primary learning modality, but audio is a great supplement during exercise, commute, and chores. Consider MLG your syllabus with highly curated resources for each episode's details at ocdevel.com/MLG. I'm also starting a new podcast which could use your support. It's called Lefner's Life Hacks and teaches productivity-focused tips and tricks, some which could prove beneficial in your machine learning education journey. Find that at ocdevel.com/LLH. You're listening to Machine Learning Applied. In this episode, we're going to talk about shapes and sizes of NDArrays and tensors. I personally found shaping to be a very confusing concept when I first started doing machine learning. It's something you definitely don't deal with outside of machine learning and data science and regular computer programming and web development and the sort. So it took me a while to get comfortable with it, and it just takes practice. So you'll eventually get it when working in machine learning. But I figured I'd do an episode and give you a lay of the land. So as a recap on something I've mentioned multiple times in MLG, when you're dealing with arrays of multiple dimensions, we call that a tensor. So an array, like you're used to, a standard array, we call that a 1D tensor, a one-dimensional tensor, or sometimes a vector. A two-dimensional array, or 2D tensor, is called a matrix. Incidentally, a 0D tensor is called a scalar, which is just a number, like the number 5 or the number 10. That's a 0D tensor. So the general term we have for any dimensional array is a tensor in mathematics. In NumPy, they call it an NDArray, any dimensional array. And we have names for 0D, 1D, and 2D tensors, that is, scalar, vector, and matrix, respectively. And there might be names for 3D and above. I'm unfamiliar with them. Instead, in the industry, we just say 3D tensor, 4D tensor, and beyond. So a tensor is any dimensional array, and in NumPy, we call it NDArray. So let's talk about the structure of these tensors. What we have is number of dimensions, size, and shape. Dimensions, size, and shape. So dimensions, like I just mentioned, are basically the number of nestings of these arrays. So if we have a list of numbers, that's a vector. If we have a spreadsheet of housing data, that's a matrix. That's a 2D tensor, so the number of dimensions is 2. If we have an image, say 256 by 256 pixel image, width by height, it's actually a 3D tensor because it also has something called channels, which is going to be red, green, and blue pixel colors. So it's width by height by channels deep or depth. And so an image is a 3D tensor. Its number of dimensions is 3. In NumPy, you might have an NDArray on hand called R, ARR. For example, a variable named R, which is assigned to an NDArray. And if you wanted to retrieve the number of dimensions associated with that NDArray, you would type r.ndim, N-D-I-M. So that'll get the number of dimensions. And you might see that performed from time to time just as a sanity check, maybe an assert statement, making sure that the input that's getting passed into some machine learning model is some specific number of dimensions because that's what it expects. For example, an off-the-shelf image classifier, namely a convolutional neural network, will typically expect to be working with a 3D tensor. And so it will assert that the dimensions of the images that you're sending to the model are 3. So it'll look like assert input.ndim equals 3. So that's the number of dimensions. Then there's size. Size is the number of elements in your tensor. So if you have a 0D tensor, aka a scalar, the size is going to be 1. There's one element in this scalar, namely the scalar itself, the number 5. There's one number 5. If you have a vector or an array of numbers, a 1D tensor, the size is just going to be the number of elements in that tensor. So if you have a list of numbers, 1, 2, 3, 4, 5, the size of that vector is 5 elements in the vector. If you have a matrix and it's a 10 by 10 matrix, well, then the size is going to be 10 times 10, which is 100. It's going to be the number of rows times the number of columns. The size is the number of elements in your tensor. So those are pretty clear. Number of dimensions and size of your tensor, those are pretty obvious. The tricky stuff is when we get into shapes. So shapes of your tensors are the numbers of rows or columns or channels, etc., per dimension. So if you have a 3D tensor, 3 dimensions, then the shape of that tensor will be 3 elements, and each element will be the number of rows or columns or whatever in that dimension. So if you have a 256 by 256 by 3 image, namely width by height by channels, picture on disk, then its dimensions will be 3, its size will be 256 times 256 times 3, and its shape will be 256, 256, 3. So the shape is the number of elements per dimension. So some common shapes that you might be working with. It's very common to receive your data from the client in the form of a spreadsheet, a CSV file. That's a 2D tensor, aka a matrix, and its shape will be rows by columns, number of rows, number of columns. So if you have a housing prices spreadsheet and you have 1 million rows, 1 million housing examples, and 50 features per house, whether they be distance to downtown, number of bedrooms, number of bathrooms, 50 features, the shape will be 1 million, 50. And the size will be 1 million times 50 or 50 million. Now, real quick, a point of potential confusion is that you'll see sometimes people referring to the number of columns in a matrix as the number of dimensions. So, for example, if you have a housing spreadsheet 1 million by 50, you'll see that 50 referred to sometimes as the number of dimensions. And they'll call this like the curse of dimensionality, when you have way too many features in your data set and you need to pare it down with something like principal component analysis or an autoencoder. The curse of dimensionality, and what specifically they're referring to there is the number of columns. Well, that doesn't stack up to what we were just talking about. Dimensions is the number of stacking of arrays in your tensor. And so in our case, there's only 2 dimensions. There's rows and there's columns in our spreadsheet. So using the word dimensions to refer to the number of features is incorrect. What they mean here actually, when they're talking about the curse of dimensionality, or when they're referring to dimensions with respect to the columns in a spreadsheet or a data set, they're talking about these columns after they've been put into the machine learning model. So when you feed your data into a machine learning model like a neural network, for example, what your neural network's going to do is take every feature per row and combine it every which way. One feature combines with every other feature. So it's a cross product of the features. So it would be 50 times 50, or 2,500 various ways that we can combine these features with each other. And since we're combining the features in a cross-product Cartesian sort of fashion, we do indeed end up in that scenario with 2,500 dimensions. So over here in the machine learning model, we're dealing with a newly shaped tensor. The data set you received is 2 dimensions, and the shape is 1 million by 50. That's all here in your left hand, and you pipe it into your neural network over here in your right hand, and the neural network does a bunch of combinations of these features, and it recreates sort of internally in its model a new tensor with different dimensions and different shape. And so when we talk about the curse of dimensionality, or the number of columns sort of representing the number of dimensions, they're kind of taking a conceptual shortcut step between your data set and how it ends up in the model. So don't let that trip you up. The number of features is not the number of dimensions. It becomes a new number of dimensions downstream in the machine learning model, but that's only after the dataset has been input into your machine learning model. So dimensions, size, and shape. And the tricky part with shapes comes when you're reshaping. when you're changing the shape of a data set. Now, normally you receive a data set from your client, a spreadsheet of housing information, for example, 1,000,000 by 50, and it's got its 2 dimensions and its 1,000,000 by 50 shape, and you pipe that into your machine learning model and everything's hunky-dory. But sometimes the shape that you received your data in is not the shape that your machine learning model wants. Or somewhere downstream in the machine learning pipeline, you have to change shapes of your data as it moves along through the steps. This is called reshaping, and it can be a little confusing. So as an example, let's talk about images. If you took your off-the-shelf convolutional neural network, CNN, sort of boilerplate copy-paste code from some TensorFlow example on GitHub, you just copy and paste some convolutional neural network code in TensorFlow and Python, you copy and paste it into a new file, and you feed it some images, okay? And it expects those images to be 3D, width by height by channels. So it wants a 3D tensor. Actually, it wants a 4D tensor. The first dimension is going to be the batch size of the number of images that you're feeding into the model at any given time. So you're going to have batch size by width by height by channels. So that's 4 dimensions there. Now, let's say that you don't have 3D images, okay? You have grayscale images. You have images in black and white. In other words, that third dimension, which is typically red, green, blue, 3 elements in the third dimension representing the color of each pixel, goes away. And all you have is width by height by nothing. You have a picture where it's width by height, and in each cell of that matrix, of that 2D tensor, is the magnitude of grayscale for that pixel. So a black and white image is a 2D tensor, not a 3D tensor. But your convolutional neural network here expects a 3D tensor. What do? That's where reshaping comes into play. Reshaping allows you to change the shape of your tensor to add additional dimensions, remove dimensions, etc. In this particular case, what you could do is force those grayscale magnitudes, the entries of the row by column pixels, this 2D matrix, you could force each cell to be an array. Because that's what you have in a 3D image. You have at each cell in width by height, at each pixel cell, you have a list, a 3-element list of color values. So each cell is an array. Well, what you could do is, in the case of your grayscale images, wrap each number in each cell in an array. So now it's a 256 by 256 by 1 tensor. We didn't add any new information. We didn't add any new numbers into these pictures. All we did was wrap the numbers in arrays. We call this expanding the dimensions, or the NumPy function for this is NumPy dot expand underscore dims, expand dims. And it will take your original tensor and it will give it one extra dimension where the shape of that dimension is 1. Namely, it will wrap the last dimension of your tensor in brackets, in square brackets. It'll just wrap them into an array. So the way you do that, like I said, is np.expanddims. But in NumPy, there's many, many ways to skin a cat when dealing with reshaping tensors or transposing or swapping axes. And so we'll talk about a number of these different ways. Expand dims is the way you simply add a one shape dimension to your tensor. Expand dims. Well, the general form of this is reshape. NumPy.reshape. That's a general function in NumPy that allows you to reshape your tensors any which way. So a common fashion you'll see reshape used in NumPy tutorials is maybe they want to show you how to work with a 2D tensor. And so what they'll do is np.arange, and then in parentheses, 100. So they're creating a 1D vector of 100 elements. And then .reshape, parentheses, 10, 10. And so it'll take your 1D array of 100 elements and it'll turn it into a 2D array of 10 by 10 elements. Same size, so you can do the reshape, new shape, and new number of dimensions. So that's a common example you'll see of reshape in practice in tutorials. But you could also use reshape to add additional dimensions, remove unneeded dimensions, and things like this. So for example, in our case, when we want to turn our image from a grayscale image into a 3D tensor, where the last element is the pixel value wrapped in an array, the way you'd do that is you'd take your tensor, R, ARR, which is an image, and you'd say r.reshape, parentheses, 256, 256, 1, end parentheses. And that 1 in the end, NumPy will know, just wrap the element. I'm not adding new information, and so the reshaping is allowed. Now let's say we have too many dimensions. For example, sometimes when I'm using a machine learning model that makes predictions, regression predictions, it'll return to me a 2D tensor. The first dimension will be all the predictions, and the second dimension, for some reason, will just be all those predictions wrapped in an array. So the shape will be, let's say, 1,000,000 predictions by 1. So it's an unnecessary second dimension. So the way you can get your predictions out of that, unpack it, remove them from that unnecessary array wrapping, is with np.squeeze. Squeeze that last dimension out. So squeeze removes one shape dimensions. So it's the reverse of expand dims. And again, the general form for all of this is just np.reshape. The reshape function is the general purpose function that allows you to perform a lot of these functions that have dedicated names. So if we had a predictions array, ARR, which has shape 1,000,000 by 1, the equivalent to np.squeeze would be r.reshape, parentheses, 1,000,000, end parentheses. No 1, no second 1. And it'll just remove that one shape dimension. Now, a little tip when you're dealing with reshaping NumPy arrays, you may sometimes see the number -1. That means wildcard, a wildcard. So if I were passing a batch of grayscale images into a convolutional neural network that wanted 3D images, okay? Just like we were doing before, we pass in a batch, let's say 32 images, of 256 by 256 images. So we've got 32, 256, 256. That's the shape of our input data. And the dimensions is 3. And we need to convert it to a 4-dimensional tensor for the convnet, 32 by 256 by 256 by 1. That last dimension just being this contrived wrapping around the grayscale magnitude. So we want to go from 3D to 4D. We want to go from 32, 256, 256 to 32, 256, 256, 1. Well, we would just do that expand dims trick or reshape, where the last argument is that added dimension. But let's say we didn't know that the batch sizes we're dealing with is 32. Let's say we know that the width and height are 256. We know the size of our images, but for whatever reason, maybe they're not stored in a variable locally, or we're doing hyperparameter optimization on the batch size, for example. The point in our code where NumPy is dealing with this tensor, it has no way of knowing that the batch size is 32, that first dimension is 32. What you can do is use -1 as a wildcard placeholder. And what NumPy will do then is say, okay, I'm going to hold off on this dimension. It'll go through the other dimensions, 256, 256, and then add a single dimension, and it'll realize at that point that it has covered all of the size requirements, converting the original tensor to the new tensor. It has enough information now to know, based on the conversion of these numbers to those numbers, what that wildcard should be replaced with, and it inserts 32 there. So -1 you'll see used as a wildcard placeholder in some reshaping operations, where you may not know the variable there, but you know all the other dimensions, and that's enough information for NumPy to infer the wildcard dimension. Okay, we talked about expand dims and squeeze. Those are inverses of each other. One adds a single dimension and the other removes it. We talked about reshaping a 1 by 100 vector into a 10 by 10 matrix. And by the way, the inverse of that is ravel, R-A-V-E-L, parentheses. That will take your 10 by 10 and flatten it into a 1 by 100. And as I mentioned, all of these operations can be generalized into the single function reshape. So reshape is sort of the only function you have to know in this broad category. Get familiar with reshape and it'll allow you to perform multiple functions. So that's shape, shapes of tensors. Now sometimes you have a different problem. You have the right shape, but some axes, some dimensions are in the wrong spot. This is a little bit rarer of a circumstance. I think you'll see this situation less commonly, but I've encountered it professionally. And the way you solve this problem is by transposing axes, or there's a function in NumPy called swap axes, and we'll compare these two in a bit. Let's frame this problem first. When you're dealing with natural language processing and recurrent neural networks and word-to-vec, you're going to want to listen to my deep natural language processing episodes to properly understand this problem setup. But in NLP, when you're doing sequence-to-sequence modeling or machine translation and stuff like this, your recurrent neural network will take a 3D tensor, batch size, let's say 32 or 64 phrases, and then the second dimension is phrase length. Okay, now what this is the maximum number of words that can occur in a sentence. So let's say that we're training this model on Wikipedia. We're trying to classify something in these sentences. Well, this dimension, the second dimension, is going to be the maximum number of words that can ever appear in a sentence. So the largest sentence possible. And the reason for this is so that this dimension can accommodate the longest sentence that we encounter. And smaller sentences will just pad the end of the sentences with these pad tokens. So the sentence length is fixed. So that's our second dimension, is sentence length. And the third dimension is the word encodings, the number of columns it takes to encode a word, using the word-to-vec model that I discussed in the NLP episodes. We call this the embedding dimension. So remember, what we do here is we convert words like cat and dog and human into a vector, into a list of numbers, which seems like an odd thing to do, but there's this magic behind it that makes it work, into a dense vector of numbers. Well, the number of elements in that vector is this embedding dimension. So let's say it's 64. So we have a 32 batch size by 100 sentence length by 34 embedding dimension, and we pipe that into our recurrent neural network. Bing, bang, boom, we have a language modeling process. Oftentimes, what you'll find is these last two dimensions, the sentence length, what's often called the time steps, actually. A lot of times you'll see the sentence length referred to as time steps. And the reason being that we're not always dealing with natural language processing. Sometimes we're using this same model on stock market predictions and stuff like this. Time steps and embedding dimension. Sometimes you'll see these two dimensions flipped. You'll have embedding dimensions as your second dimension and time steps as your last dimension. Maybe you got an off-the-shelf recurrent neural network built for working with natural language processing, and it expects time steps first and embedding dimension second. And then you take this model and instead you use it for stock market prediction. And in that case, what you get as your data set has candlestick data first and time steps second. So these two axes are flipped. You go 1, 2, and 3 in case 1, and you go 1, 3, 2 in case 2. Well, that's when transpose comes into play. Transpose. NumPy.transpose will take your array and allow you to swap axes, swap specific axes. So in this case, you would swap 2 and 3 to being 3 and 2. And it's just that easy. NumPy.transpose. You take your tensors, your first argument, And then your second argument is the new list of dimensions in what order you want them. Now, another way you can do this is with the function swap axes. But swap axes allows you to swap any two axes, which is fine in our current case. Sometimes you'll want to swap multiple axes at once. And so it's good habit to get into the practice of using the more general transpose function, which has more functionality beyond swapping axes, over the swap axes function. Just like we saw in the reshaping stuff, you can use reshape as a general function to handle expand dims, squeeze, ravel, etc. So in summary, the two core functions in NumPy that allow you to manipulate dimensions and shapes are NumPy.reshape and NumPy.transpose. There's obviously plenty more to swapping axes and reshaping and redimensioning your tensors in NumPy, but you'll get a lot of that stuff from experience on the job. I just wanted to give you a crash course on some of the heavy-hitting functions you'll see. Dimensions, size, and shape, and the way you manipulate any of these is via reshape or transpose. Reshape to insert dimensions or remove dimensions or change the shape, and transpose to swap axes with each other.